Hi, so I'm Vedant Dhruv. I'm a grad student at the University of Illinois at Urbana-Champaign. And I'm going to talk to you about low collisionality effects in black hole accretion flows. And this work is possible because of help from a bunch of people that I list out here. Okay, so when I mention black hole accretion flows, what am I really interested in? Well, our group and me by extension are primarily motivated by Event Horizon Telescope targets. So these, for example, this M87 star and Sagittarius A star. So these are the horizon scale observations that we've got in the last 5 or 6 years. And the key point that I want to really emphasize about these targets, which sort of motivates the title of the talk, is these length scales that I mentioned here. So RG is like the system scale. It's the gravitational radius. The mean free path over here is the mean free path associated with Coulomb collisions. And then you have the Larmor radii listed as well for the ions and the electrons. So the key point or the key takeaway from this slide is that you have this sort of hierarchy of scales, which suggests that the plasma, the electron ion plasmas that you're observing here are highly magnetized and are Coulomb collisionless. So this is going to be important when I talk about the model that I'll be presenting. Okay, now let me just do a quick overview of the way the Event Horizon Telescope goes about with this theoretical interpretation of these observations. So you run a bunch of GRMHT or fluid simulations of black hole accretion, and these have some independent model parameters, which has to do with the black hole spin and the strength of the initial magnetic field. So these are not known a priori about these sources, so these are free parameters. And the canonical library that the EHT uses is a single temperature fluid simulation. So you need to also prescribe the electron physics, and that's done in post. And so what you get from the GRMHT simulations is basically a time series of the fluid data and the electromagnetic fields. You then feed this into a radiative transfer code where you prescribe what is the electron distribution function, what is the temperature of the electrons, say with respect to the ions, which you can get from the total fluid temperature. So these are assumptions that you make. And then for sources such as Sagittarius A star, where you don't have a handle on the inclination at which you're observing, that is also an input parameter. So with all these input parameters, you get a whole library of images and spectra, and then you compare this with the observations and you draw inferences about the source. So you say that, okay, I have some confidence in that the black hole might be spinning in this way, and that I'm looking at it at this angle, and so on and so forth. So that's the pipeline in a nutshell. And again, the key takeaway from this is that the way the EHT goes about drawing inferences, you need a whole suite of GRMHT simulations to really come to some conclusion about the source. And that's because because of the uncertainty in the model parameters. So this, along with the takeaway from the previous slide, will be important when I sort of motivate the model later. So just a quick recap about what ideal GRMHT is. It's a fluid model. It solves these equations of motions. So you have the conservation of particle number density, conservation of energy momentum, and then Maxwell's equations. For ideal GRMHT, the stress energy tensor consists of a fluid part and of a hot fluid and of an electromagnetic term. And in particular, the fluid sector for ideal GRMHT, when expressed in the local frame of the fluid, can be written like this. So you have an energy density E, and you have an isotropic or scalar pressure. So now the idea is that you want to model a collisionless plasma, but at the same time you also want to compare it with observations. So you need to find some sort of a middle ground between fully kinetic simulations and this ideal GRMHT. So that's where this sort of weakly collisional plasma model comes into play. So the stress energy tensor now has the ideal term plus some additional contributions, and these additional contributions are sort of the leading order corrections that you get associated with the long mean free paths in your fluid. And physically, you can understand these to be the heat flux and the anisotropic pressure tensor. And in general, there are sort of 9 additional degrees of freedom that you get when you include this new physics, but making some assumptions and also using the hierarchy of scales that we have in a system, which is that the plasma is highly magnetized, we can reduce, or at least as the first step, we can consider a model, which we dub the extended GRMHT model, and we can reduce from the 9 degrees of freedom to 2 degrees of freedom. So one of them has to do with the heat flux, which is now only along the magnetic field, where you have long mean free paths. And the second one, which is a pressure anisotropy, which is a difference in pressure perpendicular to the field and parallel to the field, is the second new variable, and this has to do with viscosity, with shear viscosity. So the fluid stress energy tensor now can be expressed something like this. So it's still traceless because we don't include any bulk viscosity, that's an assumption we make, but you now have an off-diagonal component associated with the heat flux, which is along the magnetic field. And it turns out that doing this sort of a dissipative fluid model is not quite straightforward when you have relativity involved, because you have issues with causality and stability. And it turns out that unlike non-relativistic fluids, where you can just prescribe some constitutive expression for these new dissipative variables, in a relativistic setting, you have to have additional evolution equations for these new variables. There is like a whole theory about relativistic dissipative fluids and the caveats associated with it, which I'm not going to get into. But the point is that these new equations of motion make the system far more complicated, both in terms of the physics and also computationally, which I'm happy to talk about later. So we take this set of equations and we implement it in a modern performance portable GRMHT code, and then run it through the pipeline that I had shown earlier. And for this work, we focus on Sagittarius A star, and I'll get to it in a moment why we focus on this. There is an observational motivation as well. So at the end of the day, you again get a bunch of images and a bunch of spectra, which you can compare with observations. And I'm just going to talk about 2 of the results over here, the 2 main results. One, which may or may not be surprising, is that you see that the time average structure of your flow and also of the observed images are remarkably similar. And you can understand this as you can understand this in maybe 2 ways. One is that this new physics that you have introduced is ultimately only at the fluid level and not at the post-processing level, where you have the electrons and that are actually doing all the synchrotron emission. And I'm going to talk more about that later, next, to sort of motivate the second part of my talk. And the second thing is, although our fluid model cannot fully capture all the kinetic instabilities that might arise in the plasma, we have a closure prescription that sort of limits the growth of the pressure anisotropy based on both analytical and peak simulations of these plasmas. And that that tends to sort of isotropize the plasma, so the pressure is pushed towards 1 at high beta, and that could also be a reason why the images are quite similar. The second result, which I said had to do with the observations, has to do with how variable the models are. So when the EHT published the first results of the galactic center, they saw that the The GRMHT models do a remarkably good job at explaining a lot of the observations, except for one, and that had to do with how variable the sub-millimeter light curve is. And what we wanted to look at with these models was if we include dissipative terms, which are said to better approximate this collisionless systems, do we observe a reduction in variability, and do the models match the observations better? And what you're seeing here, the color and the marker type doesn't really matter, but each of this represents a model that we have, or a light curve that we get at the end of the day, and we compute a single number from that light curve, which is known as a modulation index, which is basically, if you're more familiar with X-ray astronomy, has to do with the RMS percentage. And what you see here is that most of the models lie below this diagonal line, and that suggests that the extent that the new physics sort of makes the model less variable and closer to observations. So what about the electron physics? I had mentioned that previously. That the extended GRMHT simulations, although they introduce this new collisionless terms, they only is still at the end of the day a single temperature fluid, and the electrons thermodynamics has to sort of be prescribed at the end. So it assumes an isotropic electron distribution function the way the EHT does, and we know from recent works that the electron anisotropy may have important implications for the observations. So this is work done by Lisa, which shows that when you take an ideal GRMHT fluid, but if you assume if you push all the electrons to be towards any of these instabilities, you can have differences in the observed images. And then there was also some more recent work which looked at the role of electron anisotropy in 86 gigahertz measurements of MED7. So motivated by that, we run GRMHT-informed PIC simulations. So the idea is that these are local simulations where you have a 2D box with a guide field, and you compress the plasma in the directions perpendicular to it. So you drive the anisotropy, and in particular, you drive P perp over P parallel. And one needs to pick the parameters for a plasma simulation, and that's where sort of this GRMHT-informed part comes in. So we take the image from our simulations, we compute where does the emission come from in our simulation. So this is a black hole, and this is a poloidal slice. And then using that information, we can compute what would be the relevant plasma parameters for our simulation. And we are really motivated by magnetically arrested disks, or MADs, because these are said to be the preferred state for the EHT sources. So these are low beta plasmas, and they're also transrelativistic, which has the benefit that the scale separation between the ions and electrons is reduced, because the electrons are highly relativistic. Okay, now I'm just going to talk about a few of the results that we have got so far. So one of the things that we see when we run the simulation, so what you're seeing here is a time series of the field perturbations and of the anisotropy of the species, and the magnetic field, the guide field, is along the y direction. And I think one of the points that you see here is that initially there is the onset of the ion cyclotron mode, which is indicated by this transverse parallel propagating waves. And then you also see the mirror mode, which is sort of explained by this anti-correlation in the magnetic field and the plasma density. You also see some Whistler waves at later times when the electron anisotropy begins to diverge. And the final 2 points that we see from this is that by running equivalent 1D simulations where we by hand sort of cut off the mirror mode, which is oblique in nature, we find that the anisotropy of the 2 species matches well with the 2D case, which seems to suggest that the mirror mode plays a subdominant role. And finally, despite the convergence in the length scales between the ions and electrons, what we also see is that they seem to be responding toward their own cyclotron instabilities. So what we're doing here is the red line, which is sort of hidden, is the case where both the species are compressed anisotropically, and the blue and orange is where only one of the species is compressed fully isotropically, and you don't expect it, and you don't expect it to follow this sort of dashed curve, which is adiabatic expectation. And yeah, I'm out of time, so I'm just going to leave the summary slide up there, and I'll be happy to take questions.
Okay, so time for questions. Okay, Alex always raises his hand.
In your slide on the CGL equations, you had that p perp squared over b is a constant. Why? So on your slide about not the CGL, the adiabatic invariance, you had that p perp squared over b was a constant. Why is that? Because isn't it usually p perp over nb that's a constant?
So this is the relativistic so this is a statement about not the pressure, but about the momentum of the species.
Oh, okay. I thought it was the pressure. Okay.
Yeah, sorry, I should have clarified.
Well, thanks for the talk. You mentioned that extended MHD has lower variability. Is there any way to physically understand that?
So the way, at least I understand this, so firstly, it's not a major reduction, and you don't see it across all the models. But one of the ways you can think of it, very naively, is that these dissipative effects, for example, heat conduction or viscosity, are sort of proportional to the gradient of, say, the temperature and the velocity fields. So if the variability were to have certain contributions from the fluctuations in these, in the velocity or temperature, then this sort of acts as sort of an averaging operator. But as you can see, so the observations are actually somewhere over here. So as you can see, it's nowhere close to that, and there could be a bunch of reasons why that might be happening, including some missing missing physics. So the observations would be like the average over all the days that the source was observed was 0.07. Yeah.
Oops. Thanks for the talk. One question I had was, again, about variability, but more in terms of not adding new physics, but rather going larger resolution, because as far as I understood, like with going to higher resolution, turns out that there are effects that we were missing in low resolution. Are these simulations, the catalog of simulations, is it numerically converged from just the resolution standpoint?
So what do you mean by numerically converged? In the sense of like a
how high is the Lundquist number, let's say, which we do care, say, in math simulations?
So I don't have like the explicit number on I don't have the number off the top of my head, but the simulation. So these are like simulations that are sort of like standard resolution in EHD, but they are probably which is like 384 in the radial direction.
So it's not converged.
Yeah.
Okay.
But I think it's a question of what physics that you're trying to understand when you talk about converged.
Well, variability does include some sort of flarings, etc., right? So that kind of variability.
Okay.
Yeah. Thanks. Can you say a little bit more about how you prescribe the parallel heat flux?
So we have just, so you're talking about Q?
So how do you prescribe Q?
So the way Q is, well, we don't like I said, we don't have an expression for Q. We rather solve this equation for Q that can be derived from thermodynamic principles. So there's this very rich literature about relativistic dissipative fluids, and there are sort of many ways to sort of derive these equations. And yes, this follows one of those formalisms, and if you're interested, we can talk more about it.
Just as a interesting discussion about kinetic effects, economics kinetic effects, changing Q both in local interaction.
Is the symmetry part of this equation? Sorry?
Is the subparallel symmetry part
Yes.
It's free. So it's capped off at the free streaming limit. Yeah.
So the interesting question is, beyond your very nice work, is what kinetic effects then mean.
Yeah. Okay. Okay, so I guess we're kind of running out of time. So let's thank the speaker. Thank you very much. Nice presentation.